Okay, we'll begin. Welcome to Science Friday, which is organized by Journal Club. Journal Club is an organization led by a team of students and faculty members who train new people to present, dissect scientific journals, and most importantly, provide a forum for data-based discussion. We take on almost any relevant issue that you're passionate about. If you want to be trained as a presenter, or if you're a veteran presenter looking for a venue, please email Anya and we will work with you to make that happen. I want to take a moment to acknowledge somebody on the Journal Club exec team. This week it is Sasha for her support and contributions. The team is mentored by Dr. Paul Hauser and Luke Deem. There are 3 leaders. Akshar handles the training of people on our team, Anya handles the training of presenters, and I curate and handle Science Thursday itself. This is how our meeting today is going to run. Today, Akshar is going to present for about 20 minutes. There will be time for questions in the presentation. Please type your questions into the chat. The simpler, the better. We will organize them, either call on you or ask the questions for you prefer. We are recording this presentation for YouTube, so if you would not like to appear in the recording, please do not type public messages in the chat, and only private message your questions to DU. During the presentation, we ask that you keep your cameras on and stay muted unless you are asked to clarify your question. Yes. The moderator for the discussion afterwards is Luke D, and all questions will be answered by him today, or organized by him today. Thank you, everybody, and let's give it up for Akshar.
I'll be honest, I didn't get my pep talk, so this might just be a terrible failure.
Akshar, you're going to do a great job, and the only reason to present right now is to become a better presenter. It has nothing to do with all these people that you're presenting to that are going to judge you for what you're about to do.
I didn't get the trick question. Ugh, I'm really disappointed in you, D. All right, I'm going to be presenting today about dissecting creativity. And by that, I mean expressions of fundamental constants. So for constants like pi and e, there are a variety of different ways of expressing them as an infinite converging sequence. I'm hearing keyboards. Jack, maybe you should mute. Yeah, so here are a few of them, right? The 2 on the top are called infinite series because they're sums of different numbers that eventually converge, whereas the 1 on the bottom is a continued fraction. Because as you add more terms, basically more nested fractions, you get closer and closer to pi. Now, these are all valid, but how intuitive they are can depend on a variety of things, right? Some can be proved via calculus, some need more complex methodology, right? None of them seem particularly intuitive at first, but there are surely kind of functional differences between them. Here are some for E as well. The one on the top here is one of the ways that you can define E. So it's kind of a very natural equality or convergence, whereas the one on the bottom is kind of a lot harder to see, less intuitive and harder to prove, right? So they all converge, but understanding the characteristics of convergence can be difficult. So how do mathematicians come up with them in the first place? Well, some of the mathematicians who are kind of most renowned for coming up with formulas like this rely on their intuition to do so. Ramanujan is one of the most famous. And he's credited with proposing many formulae for pi, e, and other constants. And the interesting thing is, it's not like he's reverse engineering a proof when you make a constant, when you make an infinite series or a continued fraction like this. Rather, you come up with a formula which you understand intuitively to be true, but you don't yet understand how to prove it, right? So in this context, this is kind of by definition really intuition, because it's a formulation structure and there's no proof or formal reasoning behind it. It's just you're inspired and you suddenly come up with it, right? Now, this is kind of a really amazing thing. It seems almost magical, but there's kind of a little bit of a problem here, which is that if these constants are defined before they're proved, and the mathematicians who come up with them have more understanding of how they did so than people who are watching, then how do we know what we're missing? How do we know how this intuition actually worked? Right? How can we gain a better functional understanding of what's really happening here? So that's what the paper that I was looking at was trying to understand better, which is basically they're trying to use a computational approach to find these expressions for fundamental constants, right? The basic idea, like the intuition of it, kind of makes sense. It's just to search for different expressions, which you find getting closer and closer to a constant of interest, right? The paper applies 2 main approaches for this goal. And the first is called meet in the middle. It's a very common algorithmic approach. It's basically brute force in this context, but just optimized. The second one is gradient descent, which is the same learning technique used in machine learning. And both of these are just to try and find an expression for pi, an expression for e, things we don't already have, things we do have, find patterns between them, functional differences between how computers and humans do this, etc. So first, before we get into it, there's kind of an underlying caveat here, which is the idea of overfitting constants, right? At least for me, whenever I've looked at expressions, right, the intuition of kind of contractions and infinite series is difficult, right? But you can, when you see this expression, right, it doesn't look intuitive. If there was an expression that existed like this, I wouldn't believe it to be true, right? It's pi in terms of ln, and also some of the numbers here seem a little bit random, and it is wrong, right? But it's accurate to 14 digits, and the expression looks relatively simple, right? And the reason why you can find expressions like these, which look simple, but evaluate seemingly miraculously to an important constant, is because of the kind of implicit degrees of freedom which are used when you make these constants, right? The choice to use 7/12, the choice to apply a natural logarithm, to take to the power of 1/3, right? The semantics of the expression allowed for a lot of different ranges of possibilities, even though when you finally get the expression out, it's easy to parse, or it's relatively easy to parse, right? So when we're trying to find these constants, right, and the expressions for them, we can't just bash every living thing on Earth. Rather, you want to find something that hopefully has mathematical significance and has very constrained degrees of freedom, because the more things that you choose, the more digits you need to calculate to prove that something's true, right? So the way that the paper attacks this problem is by imposing constraints on the computer search, right? So for simplicity, it focuses on just one type of converging sequence, right, which is continued fractions. And it uses a specific type of continued fraction called a polynomial continued fraction. And it's exactly what's shown here, right? So alpha and beta here are integer coefficient polynomials, right? So that means that all their coefficients are integers. You can imagine just a quadratic for simplicity, right? And then you apply that function at different natural numbers, 1, 2, 3, 4, just like you're counting, right? And those define the numerators. And then for a different polynomial alpha, the polynomial can define the denominators by the evaluations of the polynomial at different natural numbers as well, including 0, right? So on the right-hand side here, we can see an example of this, right? There are two polynomials here which derive these terms, and we get this continued fraction, right? Now, these things tend to lead to actual constants to converge meaningfully. And also, you'll notice to define a polynomial, you only need a finite number of actual terms, right? And those finite number of terms allows for infinite accuracy in what it's converging to, right? I could choose to get a million layers of my continued fraction, even though I only needed 3 terms for my quadratic, 3 coefficients to define it, right? So that allows us to actually validate, get infinite precision with only a finite number of degrees of freedom. You'll notice also there are polynomials here, gamma and delta. That's because it isn't necessarily pi, which is converged to by a polynomial continued fraction, but it could also be functions of pi, right? It could be pi squared. It could be 16/-4 plus pi squared. This is an actual formula, looking very opaque, but this system hopefully would find something like this, and actually did find this one example, and it was later proved once it was validated. So now we have search space, right? We want to be able to find, hopefully, every single, or as many possible as we can, formulas which look like this. This is called a rational function of our constant and a continued fraction, a polynomial continued fraction. And there's this quote here at the bottom. This isn't actually about a converging continued fraction, or a converging to like a constant, but it was about a problem Ramanujan solved, where the minute he heard the problem, he knew the answer was a continued fraction, and then he asked himself which it was, and the answer came to his mind, right? So it just shows the kind of miraculous, hard to like really understand method to the madness. All right, so the first algorithm which was applied here, meet in the middle, is essentially just brute force, right? On the left-hand side, right, there are a lot of different rational functions of a constant you can choose, right? Pi plus 2 over pi plus 3, or e plus 2 or e squared, whatever, anything, right? So you get a huge set and you just fill it with all of the different possible constants you could have, all right? The second step is to take all the different possible continued fractions you can have. So you just try different coefficients for your polynomials, and you get all the different things that some continued fraction converges to, right? So now you have these two huge sets, all right? And the key here is that any number which lies in both sets is a number which is both a fundamental constant and can be approximated by a continued fraction. So the intersections are precisely these continued fractions which are convergent, right? Now, intersection is a very efficient operation. You can run it very efficiently. So that's why it's called a meet in the middle. You do two different halves of your algorithm, and then you combine them efficiently.
Akshar,
yeah.
Can we just slow you down for just a second? So if you were to kind of think about this strategy in terms of very, very simple terms, what I would say is that the first kind of human strategy that you're talking about is come up with a few parameters, and then your mind kind of does the rest for you. Could you maybe give us a really quick, like 1 to 2 sentence simple explanation of the meet in the middle strategy?
Sure. Yeah. You try and find lots of constants that have some mathematical importance. You try and find lots of continued fractions, right, which converge to something, and you see which continued fractions actually converge to something special. You're basically just listing things out. The simple way of thinking about it, where it's not even meet in the middle, is you just take pi and you just test out a lot of continued fractions and you see which ones converge to pi. But the advantage of this algorithm is that it doesn't just have to be pi. It could also be e, it could be pi plus 3, it could be pi plus 3 over pi squared. And then there are a million different things you can do, but the efficiency is still retained. So you can still do it with similar efficiency. Yeah, that's the hope. Does that make sense? And I have a diagram here, which just shows the same thing. Lots of different functions of your constant yield different numerical values, right? Lots of different polynomial continued fractions yield numerical values. You check the hits, and the ones which are at least to some degree precise, you increase the accuracy for, right? And this conjecture was derived in just this way. And this is the one that I showed from earlier. It wasn't known until this paper ran their algorithm. It looks very simple, but no one had ever thought of it before or proved it. It's now been proven. And it was used by the same process, right? This here is kind of a simple polynomial of just negative x, and this would be x plus 3. And you evaluate two polynomials, and you get exactly this, right? So I guess that's how the process works. Any questions on that?
Yeah. There's a question from Wes. How do we increase the precision of how do we do the increased precision step? Sorry.
Yeah, so you start out with a first space, right, of coefficients. You can do that however you want. Like,
could you go back one slide, Akshar?
For instance, you could maybe this one's better. For instance, you start with some search space of coefficients you check, of polynomial continued fractions you check, right? Once you get your hits, then you can just increase the number of digits you crank out. So I had pi to 100 digits, let's say, and I had a continued fraction to 100 digits, and they worked together, and then I just make it 1,000,000 digits, because now there are much less, right? Before we had a million things to try. Now we just have 3 hits that we can spend a lot more time on. So it's exactly how you'd think. You just calculate more terms.
Any others from the audience? And don't be afraid to ask simple ones. And if you have a simple one you want to just chat me privately, you can do that. I think we're good.
Awesome. All right, so the second algorithm that we're going to be talking about is called descent and repel. And this is the algorithm they developed. It's based on gradient descent, which is a technique which is often used in machine learning. That's the most common usage of it. And the basic idea relies on something called a cost function, which kind of estimates how much error you have and tries to minimize that, right? And the hope is eventually you'll have 0 error, which is the best case, right? So these cost functions can also be called loss functions. And the paper uses 2 different loss functions in sequence, all right? This first one, in terms of all of the coefficients of your polynomials, right? if each of these was a quadratic, that's 3 coefficients, because there are 3 coefficients that describe a quadratic per polynomial. So in terms of those 12 numbers, you calculate the error, right? So hypothetically, if you had a continued fraction which converged to a constant, this would be 0, right? So you start out with some random terms and tweak them all so that you can decrease the loss function. The goal is to decrease the loss function, because if you got a loss function of 0, you've won, right? You'll note that this kind of process of tweaking doesn't really work with integers, right? You can't tweak integers by a small amount. You can only tweak real numbers or rational numbers by small amounts. So the second step tries to project everything onto a lattice. So if a number is far away from its rounded version, then there's more error, right? So not only do you want your number to approximate the constant well, but you also want it to have integer coefficients, the polynomials. So if this were to work, then your loss function would eventually reach 0. Now, it's very important to notice that this is not kind of a trivial thing, right? Sure, gradient descent can be used, but in machine learning, it's often a heuristic, right? What that means is that it isn't supposed to be a perfect solution. It's just supposed to decrease error as much as possible. But in this case, you need a loss of exactly 0 or it's completely useless, right? It's an all or nothing situation, right? So it's only due to the structure of solutions, which they go into in more depth, and maybe if we have time, I can show a little bit of that. But it's only because of the structure of solutions that loss 0 functions were, that loss 0 approximations could be found in this way. There's a second step, which is why it's called descent and repel. And this step is essentially, we have 12 different numbers, right? Our polynomial coefficients, which describe an approximation. And what we can do is, Jack, I think you might have unmuted. And what we can do is we can make those points, those n-dimensional points, in this case 12-dimensional points, repel each other, right? Imagine them as 2 like charges, right? 2 point charges, for instance, which are both positive, and they'll repel. That way, all of our different hypotheses for different approximations will have distance from each other. They won't all be the same. I see a question. How do you know that your RHS hits aren't converging to something very close to your LHS expression, right? So it's a good question, right? And first of all, you can't know for sure, right? This whole thing is supposed to be a numerical approximation, so you always need to prove it afterwards, right? But if you remember, right, our RHS hits are defined by polynomials, and we can determine as many terms as we want of the continued fraction, right? So I could calculate the continued fraction to 1,000,000 digits, and I could calculate my constant to 1,000,000 digits, right? And if they still agree, it's unlikely that that'd just be an artifact of something, right? That at 1,000,000,000 digits, it would suddenly diverge, because I only defined, like, the number of things I chose was very small. I said like 3, 5, 6, 7, -1, 2, and suddenly I'm getting pi, right? So it's unlikely that something like that would happen when I have infinite precision to validate. Does that make sense?
Akshar, we also have I would say a kind of higher up question. What is the utility of what you are describing in kind of as a whole?
I'll get to that. That's like a coming section. I also saw one about, I see 2 above. I see why is this helpful? I'll get to that, yeah. What level of precision is useful for practical applications? I'll kind of get to that as well. A lot of the approximations people do of pi, for instance, like to trillions of digits, are useless. There's no real practical application to them. It's basically kind of just flexing. But I mean, it's an interesting theoretical question of how we find the fastest approximations, right? And I guess any applications to this paper are also applications of levels of precision. Anyway, I'll get into that more. The second question is, are there intuitive ways to understand these continued fractions? For some of the easier ones there are. I don't know a lot of this stuff because I'm not like kind of great at it, or I'm not like that much into math. Some of it's pretty complicated math, but one kind of easy idea to understand, like one easy proof of why continued fractions might be useful, is if I were to give you something like this, right? Then one proof that you can use for these guys, because this one's simple enough that it has an easier proof. One proof you can make for this kind of thing is to note that 1 divided by x minus 1 is equal to x. If you think about it for a second, right? 1 over x minus 1. So, did I do that wrong? I did that wrong, didn't I? 1. Oh, yeah. I meant 1 over x. Sorry, that's my bad. I meant 1 over x minus 1. Because if you take the reciprocal of this value and subtract 1, that's basically the same as crossing all of this out. And the remaining thing you have is exactly the same as what you started with. So that's an intuition for how you can prove some of these formulas, because from this thing here, you can solve for x. And I think it's phi, if I'm not mistaken. But for some of the more complicated ones, it's much harder to figure it out. And yeah, but I mean, that's a little bit of intuition if that helps. All right, okay, I'll move on for now. So some of the results, right? It's still happening right now. They basically made a website where they show all of the different formulas they found and ask mathematicians, please solve these for us. Because even if it's incredibly likely that these things are true, mathematicians want to prove them for the sake of rigor, right? You can keep on going with this. You can choose different constants to try to approximate. You can change the polynomials you're guessing with. You could veer off of continued fractions and use different algorithms, right? There's a lot of potential here because the techniques used are very general, right? There isn't anything too specific to this approach or to this application. So here are two examples, which I've shown before. This is an example of a very simple one, which people have overlooked. And this one is kind of more complicated. You can kind of understand why this wouldn't first come to mind for most people. But both are true and both have been proven by mathematicians who saw this paper and its results. Oops. Oh my God, what happened? All right, here's questions again.
I don't think there's any new ones in the chat, Akshar. If I'm missing one, please somebody just quickly shoot it again.
All right. So now I'm going to be talking about applications, right? The first one is approximation, right? The only way you can approximate numbers is by having these convergent sequences or series, right? I mean, you could imagine that the most obvious way of computing pi is just to make a really big circle, measure its circumference, and divide it by its diameter, right? But that isn't the most efficient way of doing so. And approximations to pi, which might not seem intuitive, have incredible applications to being able to approximate different constants, right? I think Newton, with his applications of calculus, was able to find far better approximations to pi than anyone before him, because they would use approaches which kind of fit polygons within a circle and used their areas to calculate pi. So how exactly do we classify how good approximations are? Well, there are two classes that we can consider here. The first one is kind of exponential. You can imagine an exponential approximation to mean that there's kind of a digit to term ratio, right? So fraction depth here means how many layers in the continued fraction you go down, right, before you stop, right? So what it means to be exponential is that if you give me there's some kind of constant relationship between the number of terms in the continued fraction you approximate and the number of digits of pi I know, right? So if I know 1,000 digits of pi, and then you double the depth of your fraction, I can know 2,000 digits of pi. If you triple the depth, I can know 3,000 digits of pi, right? And even if I'm 1,000,000 digits into pi, it's just as easy to get the next digit. And this is kind of exponential convergence. So here it shows log error. If this was just error, the convergence would be more of a very steep curve, which goes infinitely close to zero, right? Because getting a number to 1,000,000 digits of precision is incredibly accurate. It's more accurate than you would ever need to know. This is the polynomial convergence, which is the alternative to exponential convergence. The idea here is that the more terms into pi I get, the harder it is to get the next one, right? 1,000,000 digits into pi is harder than 100 digits into pi, right? So polynomial convergence is worse, of course, and the best approximations for pi are exponential, right? Now, one of the interesting findings of this paper is that every single approximation found by the computer was in exponential or better time, whereas a majority of those found by real life mathematicians are polynomial. So that demonstrates some kind of functional difference between the types of formulas that computers find and humans find, which is very interesting, right? It's potentially more interesting than if it was identical, because that gives us some kind of thing that humans must be missing, and shows us some of the features of the different continued fractions that we find, right? Secondly, if we find faster approximations with computers, that means you might actually eventually find a faster approximation for pi than we even know today, and be able to find even more digits potentially. And concretely, the paper was actually able to find some of the fastest approximations for a constant called Catalans constant. And so let me just explain this graph right here. Each term in a continued fraction, right, can be really complicated. It can have big numbers. It could require a lot more kind of computational power, right? So that's what the compute degree means, right? How much each numerator and each denominator, how big it is, how complicated it is. Terms per digit is what we were talking about before. If it takes 5 terms per digit, that's much worse than if it takes 1 term per digit, right? So this part down here is the best possible algorithm. It means that every single term in our continued fraction is very simple, and you only need a few terms to crank out many, many digits of a constant, right? And you can see all of these new ones are the ones that the paper found, and they are some of the best that have been found, right? Because this one, although it has a very high compute degree, is very efficient in terms per digit. And this one right here is kind of a compromise between the two, but they're better than the ones that used to come before them. So approximations can be improved with this method. A second reason why this kind of thing is important is called an irrationality measure. An irrationality measure is a reason why something like a continued fraction can actually really prove something that's theoretical, which is kind of interesting because we usually think of computers as only to do numerical bashy stuff, but this is an example of a theoretical application. And it relies on this concept called an irrationality measure, which tells us how irrational a constant is, right? In a very informal sense. Every rational number has an irrationality measure of 1, all right? Which means that if I can prove that the irrationality measure is greater than 1, then I know by necessity that a constant's irrational. And because continued fractions provide more insight into the irrationality measure, they can help you prove a number's irrational. For instance, this paper was able to find a lower bound for the Catalans Constant's irrationality measure at around 0.56, right? Which is higher than any other lower bound found before. You could imagine a situation in which computers are so sophisticated in their algorithms that you can prove any numbers irrational in a second, even though mathematicians haven't been able to do so for hundreds of years. It's still an open question if Catalans constant is rational or irrational. All right, so for some conclusions, the paper offers a first glance at how computers can derive formulas for fundamental constants, right? This is just a first glance. There's a lot more to come from this. There are many different applications, and it's very much still kind of an open effort. And it's cool that such relatively simple methods are effective. I say relatively simple because they're kind of the first two things that come to mind when you talk about these things, right? The first one is just trying everything as fast as you can. And the second one is kind of machine learning, which is a hot topic right now. And as long as you can ensure that overfitting is prevented, there are formulas to be found. And finally, apart from the applications of the actual formulas you find, we can help probe mathematical intuition and find out, of all the continued fractions that exist, what do mathematicians find? What can they find? And potentially, what insights do they actually have when they say this formula exists or this formula exists? So it helps deconstruct some of the troubles that every single one of us has with wondering how the heck do they do that when you see all these weird formulas, right? I feel like in math, people often do that, right? In math classes, to impress you or to astound you, they give you formulas which you have no idea how to solve, which, I mean, is just as impressive as it is kind of incapacitating in that it's harder for you to do stuff if you don't understand it, right? So this offers another recourse to understanding what we don't about how we do math, kind of meta. Yeah, that's all. Any questions?
Yes, Akshar, thank you very much. From Wes, how do we calculate the reference value for computing error?
You mean like, what do you mean by that? Do you mean like, how do we calculate how much precision we need to ensure that our approximation isn't fabricated?
Wes?
No, so the question I'm asking is, so what we do is we're computing an approximation, right? And then we say, how far off is this from actual pi, right?
Oh, you mean the reference value for, I see.
Yeah, like how do we know, like how do we actually calculate pi to a trillion digits so that we know that our approximation is accurate out to not a trillion digits?
That's an interesting question. Let me think about that for a second. So, I mean, presumably you could just say take the best approximation of pi. That's probably the best one. But how off is that? I mean, my first thinking is that it doesn't matter. That as long as you're a few digits more accurate, that the distinctions in error are basically insignificant, and that the kind of exponential or polynomial trends of convergence will still persist.
So I'm confused though, right? Like so right now we say we have some algorithm that is the best approximation for pi that we know, right? And then let's say I find a new one and it starts to diverge at a trillion digits. How do we know that my algorithm is not more correct than the existing one?
Oh, I see something that Akshay says about spigot algorithms that give the nth digit of an irrational number. There is something like that for pi. I think that it's not in base 10 though, it's in base 2, if I remember correctly. That's a good example, but more generally, I think that kind of if it reaches a stable state in a given digit, you can confidently say that that digit is correct, right?
Well, it still sounds like you have a question. Do you want to? Oh, go ahead, Willow.
Yes, we have an all-school meeting in 2 minutes, which is mandatory for students. So I think it's time we end this meeting. Akshar, being a student himself, means we cannot continue this meeting for the adults. If you have any questions, please email Akshar. I'm sure he's happy to answer any questions. We hope to see you next week with Ted's presentation. Thank you, everybody, for coming.
Thank you.
Also, Wes, I think if
Thank you.
a given approximation is proven analytically and a digit stays the same. Oh, no. Okay, so an approximation is proven analytically. I'm sure there are ways in continued fractions. It seems more obvious in infinite series, but I'm sure there are ways in continued fractions to give upper bounds on how much they can change with the new terms, right?
Akshar, just so you know, if you want to stick around for a little bit, I'm sure that's totally fine.
Yeah.
Also, I'm guessing that if it is like, this is why there's the analytical step in the end. Like you try to converge as far as possible. And if like that's it, then they check it if it like analytically converges. And if it does, then they're gold. The idea is that the algorithm will give you new pathways that ultimately humans still have to verify. Is what I'm guessing why they don't care as much about what the reference is.
I mean, I suspect that if you have one which is proven and you have it 50 trillion digits, then it doesn't matter. Your graphs of exponential convergence, polynomial convergence will all look effectively the same as if you actually have.
Oh, right. Of course. So you come up with the polynomials, you approximate it out to some large number of digits. Like it doesn't even have to be a billion; it could be like 1,000, right? And then you say like, oh, okay, I think this is an approximation. And then you go up to mathematicians and you say, hey, can you prove that this actually is correct? And they say yes. And then you can take your approximation, which you now know to be correct, and see how many terms you get with each additional digit.
Yeah, and also calculate like statistics of the continued fraction to find irrationality measure.
Right. Like terms per digit, and you can do all that good stuff. But the first thing you need to do is have a human actually prove that your continued fraction is in fact not an approximation, but is exactly the thing that you're trying to prove. Right.
It seems we still need humans after all.
Only for now, Ted.
Yeah, not for long.
Until my talk next time.
All right, thanks so much, Akshar. This was fun.
Yeah, thank you, Akshar. That was one of the best presentations I think this year.
Good job, man.
Thank you.
Bye. Have fun. All right, thank you, D.